Good morning, dear students. Welcome to our session of Communication Lab. So, in the previous session, we discussed and we saw execution with respect to Simulink, in which we look forward for NRZ and RZ representations, and then we saw how we can implement pulse code modulation, that is indirectly sampling and quantization. So these are the two aspects what we discussed. That is the two experiments what we discussed in the previous session. So moving ahead, uh, in Simulink, right, we need to implement ASK, FSK, and PSK. Using Simulink, we'll be looking forward to implement ASK and FSK first, and then we'll look ahead with the rest of the things. So what is amplitude shift keying and frequency shift keying? Now, if you remember in your analog communication, you had come across few aspects like amplitude modulation, which you termed as AM, then frequency modulation, which you termed as FM, and phase modulation, which you termed as PM. So similarly, again, you had different specifications, what you had looked out. So these were the things what you had discussed. So what is basically modulation? So modulation, when you consider, right, if you have raw information, say there is a sine signal, say this is the voice message which is present. So generally your voice message will be at low frequency. It will be say in the audio frequency range. Now, if I have to transmit this information to a long distance, what happens is if I transmit it in its raw form, it will travel only a shorter distance and it will say fade off. Now, if I have to transmit this information to a longer distance, then how do I go ahead? What I have to do? So it is like you have a paper and you have some information written on this. So this is nothing but the sign information, what I am specifying. So you have some information and this paper, if you throw it, say you fold it, you say scramble it, and then you throw it. What happens is it will travel a short distance and it will fall off. It will fall off. But can I make this paper to travel a little bit longer distance? I can do this if I make use of, say, a stone, and then on this stone you wrap this message. So message is not disturbed. Message is not disturbed. You wrap this message onto the stone, and then you throw the stone which is having that message. So what happens is the stone will help this message to travel a longer distance as compared to when the paper was alone thrown. So here the same concept I can apply even for messages. So which is done in modulation. So here if you just saw, paper is of lightweight and stone, when we compare, is of heavyweight. So here the paper in a communication has to relate to the message, and the stone has to relate to something we call as carrier. So here also it is, the stone is acting as a carrier of whatever message is present in this paper. So in the same way, even in communication, we have these two concepts. So we have a message and we have a carrier. And on this carrier, I give a ride to this message. So how do I give that ride? I give that ride with the help of modulation. With the help of modulation. So it is like you're taking the paper and wrapping it around this stone and throwing it. So that itself will be called as modulation. But in terms of your communication aspect, what this has is, you have the carrier signal. We term it as the carrier signal, which we can say represent as C of T. And then you have a message signal. So if it is a there are again two types, whether the message is continuous, that is analog in nature, or whether it is digital in nature, that is whether it is just zeros and ones. So in short, if I I'll just consider as a message signal. So when I consider the message signal, what happens is this carrier has some of the features, like it has frequency, it has phase, it has the amplitude. So whenever you consider a carrier signal, whenever you consider a carrier signal in communication, it has frequency associated with it. It has frequency associated with it. It has the amplitude associated with it, and it has the phase information, like at what phase it is starting. It has some phase information pertaining to this. So now what happens in modulation is the carrier's characteristics, that is, these are the characteristics of the carrier. So you alter some of the carriers and the others you keep it as it is. So how do you alter? You alter with the help of this message. So here, if I consider a message signal, if I consider a message signal and alter the characteristics of the carrier signal, then I get the concept of modulation. Now here, when we are performing this operation, we have to keep one thing in mind, which we call as the Shannon's modulation condition. Sorry, not the Shannon's. It's the sampling. Sorry, not the sampling. It is the modulation condition. So here, if your message signal, if your message signal consists a maximum frequency of FM, consists a maximum frequency of FM, and if the carrier frequency is FC, then if I have to modulate a signal, then I should keep in mind the modulating condition. That is, FC what you're choosing, or what is the carrier frequency, it should be greater than equal to 2 times FM. So if you're satisfying this condition, then what happens is at the receiving end, you'll be able to recover the message what was wrapped around the carrier, or else it becomes difficult to identify what was the message. So for example, you have a stone which is big enough, and you have a you have a paper over here. Now if you are not able to wrap the paper around this, then what happens is you might lose this information in between. So it is something related to that. So carrier frequency should be greater equal to 2 times FM. That is where FM is the maximum frequency of the carrier, message signal. So this condition has to be satisfied. If this is not satisfied, then we get what is known as undermodulation. We get what is known as undermodulation. So this is the concept what we utilize when we are dealing with modulation. Now, when do I call the modulation to be digital and when do I call it to be analog? So if the message signal is analog, if M of t is the message, that is the message signal is continuous or analog, and this message signal is altering the properties of the carrier, then I call it as analog modulation. Now, if this message signal is a bit stream, that is, it is zeros or ones, and if this one is used to alter the characteristics of the carrier signal, then we classify it as digital modulation. So here, if you remember in your previous analog communication subject, you might have come across analog amplitude modulation, frequency modulation, and phase modulation. So when you're dealing with continuous signals or the analog signals, we classify these modulation techniques as analog modulations. Now, if the message is zeros and ones, then we classify them as the digital modulation technique. So here just a few techniques are specified. So we can have amplitude modulation. Under that, again, we can have PAM and QAM, that is pulse amplitude modulation and quadrature amplitude modulation. Then phase modulation, so we can have phase shift keying, differential phase shift keying, then orthogonal phase shift keying. Then frequency modulation, we can have frequency shift keying, and these are all under digital modulation techniques what we are specifying. So these are just a few things to name around. So now next, what is actually ASK? So ASK is amplitude shift keying. Now ASK is actually a digital modulation technique. Now, why it is a digital modulation technique? Because the message what you are considering will be in terms of zeros and ones. So the only possible values will be 0 or 1. And in previous session, we had seen that how we represent the digital information with say NRZ and RZ formats, polar, bipolar. So that is what we'll be considering. So now message will be in terms of zeros and ones. That is, the information will be in the form of bit stream or digital in nature. Now, what does amplitude shift keying imply? Now here we can see that this is the message signal. This is the message which is zeros and ones. And this is how it is represented in one of the formats. Say we'll consider it as non-return to zero, you say unipolar format. So here it will be like plus say 5 volt or plus 1 volt. That is, this is logical high, this is logical low. So that is how you consider it. So here we have zeros and ones in the message signal or the bit stream. And this is the carrier signal, that is what we are considering. And carrier signal frequency should be satisfying the condition. This condition has to be satisfied. So now here we are considering the carrier signal. Now what happens in amplitude shift keying? Now the name itself tells that you have to alter the amplitude of the carrier with respect to the message signal. So you have to alter the amplitude of the carrier with respect to message signal. So in digital data, what happens is for the given bit duration, this value will be same throughout that entire bit duration. So if it is say plus 5 volt, if you're representing that as plus 5 volt, this will be entirely plus 5 volt. And if this is 0, it will be like 0 volt. Or it might be, if you're representing it in the other form, it might be minus 5 volt. So if you just observe, there is only two possible levels over here, because you have only two possible representations, that is 0 or 1. Whereas in analog, what happens is you can have amplitude in any form. It can take any values in the given range. Amplitude can take any values in the given range. So now in this case, so what has to be done is how ASK will be implemented is, if the message bit is 1, if the message bit is 1, you do not disturb the carrier and send it as it is. That is, you maintain the amplitude of the carrier throughout the bit duration. Throughout this bit duration. So that is what you can see here. The carrier, the same carrier will be present over here. If the bit is 0, then what I do is I suppress the amplitude of the carrier in this given bit duration. So here you can see that this is the carrier which is continued. But what has to be done is, since this is logical 0, its amplitude has to be made 0. So here what has happened, you are changing the amplitude of the carrier. You're changing the amplitude of the carrier. So similarly, again it is 1. So you maintain the amplitude of the carrier now again. So that is what is shown over here. So again it is 1, you maintain the amplitude. Again if it is 0, you suppress the amplitude of the carrier to 0 volts. To 0 volt. So whenever 1 is there, so in short, if we speak in layman's point of view, if it is 1, you send the carrier as it is in the given bit duration. That is, you maintain the carrier as it is. If it is 0, you make the carrier amplitude 0. So this is amplitude shift keying. So if you just observe here, the message which is there, it is either 0 or 1. So this 0 or 1 is used to key in the amplitude of the carrier. Either the carrier is present or it is absent. So you are basically utilizing this one to alter the amplitude characteristics in this. Only these two possible values are there. So you'll be using only these two values, either on or off. It is like this is like the on condition, this is like the off condition. So whenever it is either of this, you key in only the amplitude of the carrier. When 1 is there, amplitude of the carrier is present. When it is 0, there is no amplitude of the carrier. So this here you are altering just the amplitude. But what about the frequency and phase? You are not altering the frequency and phase of the carrier. You are maintaining it as it is. Only thing what you're altering is the amplitude. So when it is 1, you are maintaining it, and when it is 0, you're suppressing it. So that is what you're doing. So this is amplitude shift keying. So when this information is transmitted and received at the receiving end, that is the receiver, what receiver does is it tries to see in the given bit duration. So this is the bit duration what you are having. In the given bit duration, what is the energy which is present over here. So if you just see, energy will be say some energy value will be present since carrier is present in the bit duration. So if that is the case, then it gets to know that it is a logic 1 which is over here, and in the given duration, if the energy value is very low, then it gets to know that it is a logic 0. So this is how it continues. So if there is a carrier present in the given duration, it is logic 1. If there is no carrier, it is logic 0. So this is how the receiver will try to estimate what has been transmitted. So this is the logical aspect what we have to look out to implement ASK. Now moving ahead, next one is FSK, which is frequency shift keying. It is frequency shift keying. So again, here we consider the data to be FSK is a digital modulation technique, because the message what will be used will be zeros and ones. So in this case, we are considering the message as zeros and ones, and this one is the carrier signal. This one is the carrier signal. Now in this case, what logical implementation is done is, you can observe, whenever the data is 1, that is the bit is 1, what you do is you send the carrier with high frequency. That is, you alter the frequency of this carrier and send it. You make the frequency of this carrier a little bit higher and send it. So here you can see that the frequency in this bit duration is higher. You are increasing the carrier frequency when it is logic 1. And when it is logic 0, you alter the frequency of the carrier to be lesser, to be lesser. So that is what you are doing over here. Whenever it is logic 1, you alter the frequency of the carrier at the higher end, and whenever it is 0, you alter the frequency to the lower end. So you reduce the frequency of the carrier when it is 0. When it is 1, you increase the frequency of the carrier. So that is what you are seeing over here. Now since only two possible values are there, what happens is you'll be having only two possible frequency changes. Whereas in continuous signals, what happens is you can have different variations of the frequency. Now at the receiving end, what is done is the receiver checks in the given duration what is the content of the energy which is present over here. For high frequency content, what happens is more amount of energy will be present, whereas for low frequency of the carrier, less amount of energy will be present. So if the energy is higher, it will be identified as logic 1. If the energy is lesser, it will be identified as logic 0. So this is what is done in frequency shift keying. Now here, if you just observe, only the frequency of the carrier is altered, whereas the amplitude and the phase information of the carrier is unaltered. So in FSK, only the frequency parameter is altered, whereas amplitude and phase parameter is unaltered. In ASK, amplitude parameter is altered, but frequency and phase information is kept intact. That is with respect to the carrier. So this is with respect to ASK and FSK. Now you have another concept which is pertaining to phase shift keying. So PSK refers to phase shift keying. So what happens in phase shift keying? So the name itself tells that you have to alter the phase of the carrier, keeping the amplitude and frequency of the carrier unaltered. So here again you have 1, 0 and 1, and this is again digital modulation technique, because you will be using the message which will be, or message or data which will be in terms of zeros and ones, that is in terms of digital. And here you are considering the carrier signal. So here if I just draw this line over here, right, so you can see what is actually happening over here. So this is 1 bit duration what we consider. So here it is logical 1. Now when it is logic 1, what, or when it is bit 1, what should be done, and when it is bit 0, what should be done in PSK. Now since only 2 possible values are there, whereas in the other cases what happens is there will be in that is analog phase modulation, there are different values of analog signal is possible. So therefore we have to be careful when we are dealing with those aspects. So here we can observe, so whenever it is logic 1, or if the data is 1, so if I consider that this is the carrier where it is this is the carrier, and if I just observe, if you just make an observation, if I have a carrier like this, so if this is my carrier, uh, and a carrier which is unaltered will be in the same way, that is it will be starting at the same point. And if I have, say, if I have to consider a carrier which is 180 degrees out of phase, so what should happen? If you just check out here, this has to be altered by 180 degrees, so which is actually this signal. So this is 180 degrees out of phase with respect to the carrier. This signal is actually in phase with the carrier. So now I make use of these two aspects. So one for 0 and the other one for 1. So that is what I'll be looking forward. So in this case, what we are doing is for logic 1, we can consider the carrier phase to be unaltered. When it is logic 1, don't alter the phase of the carrier during the given bit interval. So that is what is being displayed over here. The carrier phase is kept intact. That is, phase of the carrier is 0 with respect to the carrier signal. So phase of this one is 0 with respect to this carrier signal. Now when it is logic 0, now in this case what we do is we transmit, or we consider carrier which is 180 degrees out of phase. So here you can see that this carrier signal is continued. So it is the same carrier signal. At this point, if you can see that it is continuing from this location. So 180 degrees out of phase will be just opposite to this. So it will be like this. It will be 180 degrees out of phase. So this entire carrier will be 180 degrees out of phase. So here this signal is transmitted. So whenever it is logic 1, the carrier phase is kept as 0 degrees. That is, it is unaltered. But whenever it is logic 0, you alter the phase of the carrier with 180 degrees phase shift. So again, there is logic 1. So here what we do is we maintain the phase of the carrier. So here this carrier, if you just observe, it is continued, and its phase is in this form. That is, it is starting like this. So here, when it is logic 1, you don't alter the phase of the carrier. You keep it as it is. So this is what you implement in PSK. Okay. So this is what is happening. So here you can see that if this is the carrier signal what we are considering, then C dash of t is the phase inverted, 180 degrees out of phase. So if this is the signal, if this is the carrier signal, 180 degrees out of phase signal will be appearing like this. So therefore what happens when it is logic 1, you transmit in phase, that is C of t in phase, and whenever it is logic 0, you transmit the out of phase. So that is what is being done here. So at the receiving end, you have to identify the phase of the signal. So here, if you just try to measure the energy, it will be same. So you have to have an indication of what is the phase of the signal in the given bit duration. That is the phase of the carrier signal in the given bit duration. Based on that, you decide whether it is logic 1 or logic 0. So that is what you look out for. So this is from logical point of view. Now let us look at the Simulink part and see what results we can obtain. So here already I had created a file for ASK and FSK, so that I'll be just showing. So in order to do this, what we can have is, so if you want, I can have a new file and just check out. So in order to implement this, first you should have a Bernoulli binary generator. So this part will be acting as what? It will be acting as the message signal generator. It will be acting as a message signal generator for me. So here I'll consider, so I have a Bernoulli binary generator, which is actually under communication systems toolbox. Under that, communication sources, random data sources. So I have Bernoulli binary generator. Now after Bernoulli binary generator, if the data is 1 or 0, that is what I have to identify. So that is what is done over here. So I have to identify whether the data is 0 or 1. And based on that, I should perform some operation. I should perform some operation. So what is that operation? So in order to do that, I should use a switch. I should use a switch over here. So this is the switch which I have, and these two have to be connected. So what is this switch doing? It is trying to check whether it is a 0 or 1. So if I have to alter the condition, I just double click this block, and the threshold what I'm setting is 0. So if the threshold is greater than 0, then whatever is connected at this point will be selected, and if it is 1, if the condition is false, whatever is connected here will be considered. Okay. So now what I do is in ASK, I make use of, so here you can see that there is a sine wave. So now here what I do is I use the sine wave source. So I make use of the sine wave source over here. And this one I'll connect it at this end. So what is this telling? This is giving us that whenever this data is 1, that is greater than 0. If it is 1, that is logical 1, then whatever is connected over here will be presented at the output at this point of the switch. Now I want another block of the sine wave. So we are assuming that these two sine waves are same. It is the same. So now here, this one we connect it at the other point of the switch. So now here let us see what is the result we will be getting. So in order to do that, I use a scope. So now here what we'll do is, so I'll first see what the sine wave is generating. I'll first just check out what the sine wave is generating. And then next I'll try to connect and see what is this output that is being generated. So I haven't changed any parameters over there. So I'll just save it. Okay, I have just saved it. So ASK under test one, I have just saved this. So let us see what result I'll be getting when I run this Simulink. So this is, I'll just double click the scope. So here you can see nothing. So just try to change the layout. So here you can see that no major changes are there. So another one thing I'll just connect. I'll try to connect I'll increase the ports to this. I'll make 3 ports. So what I have done is, okay. So now again I'll run it. Double click. I'll just check out. So here you can see that Bernoulli binary generator is generating the parameters. I'll just name it. Okay. So I'll just replace the names. So this is the binary generator this thing, which is your message signal, and this one is your carrier signal, and the switch has to give me the ASK output. Okay. So this is a message signal. This is the sine signal, and here we can see the ASK output, but I am not getting the expected output. When it is 1, the carrier amplitude should be unaltered, but when it is 0, there should be no carrier. That is, the carrier amplitude should be 0. So now let us see what changes we have to make. Okay. So I'll just double click over here. So let me see. I'll just increase the frequency. I'll make it around say 20 radians. Okay, phase is unaltered. Nothing. Let the amplitude be same. So now, since this is also same, what we have to do is, in this case, what happens is there should be nothing appearing at the other end. So I'll make the amplitude 0 of this. So if I make the amplitude 0 of this, so let me see what I'll be getting. So it is indirectly like connecting to the ground. So let me see whether I'll get any So you're getting some information over here. When it is 0, amplitude of the carrier is suppressed. But when you're increasing the frequency, you can see that some distortions are happening. So here you can observe what is present. When it is 1, carrier signal is present. When it is 1, carrier signal is present. But when it is 0, it is not present. So let me see what changes we can still look forward. So what I'll do is I'll just try to say change the sample time. So since here what happens is you are taking the samples from the system and then you are generating the sine wave. Because of that, the distortions what you're observing over there will be seen. So I'll just make it 0.01, 0.01. So even this one, if you want later, if I have to utilize, I can utilize it. But it's since it is 0, right? So no need to worry. So here I have changed the sample time. So let us see what happens in the scope. Okay, somewhat I am able to get the sine wave representation. So now here you can see that in the given bit duration, if the data is 0, the carrier amplitude, this is the carrier signal, the carrier amplitude is suppressed. So here it is 0, 0, the carrier amplitude is suppressed. But when it is 1, we are having the carrier amplitude unsuppressed. That is, we are sending it as it is. So whenever it is 1, carrier is present. Whenever it is 0, carrier amplitude is suppressed. So this is, now you are getting the ASK result. Now next what we do is using this logic, can I implement, can I get back the original information? Can I get back the original information? So if I just happen to cross check this, so here you can see that some changes we had done, some changes which are present over here are being done. And here we have the other stuff. So now let us see what logic it will be providing when we multiply these two aspects. So here we are getting the ASK output. Once I have got the ASK output, now what I want to do is using this, can I get back the original information? So let us see what we'll do is we'll make use of a product block. So what this block will be taking the product of, it will be taking the product of the ASK output and this carrier signal what we are specifying over here, I'll paste it so that I want to retain the properties of this carrier signal. So this one I'll consider and attach it to the other part. So here I'll be getting some product. So let me see what is this result. So still I haven't completed it. So let me see what is the result over here. So I'll change the layout. I'll run it. So here you can see that some changes are happening. Some changes are present. So here what you have done is you have taken ASK result and multiplied it with the carrier signal. So whatever is present over here, so this and this you have multiplied. So when you do this, what is actually happening? So if you look at the amplitude, if you look at the amplitude parameter, so if you just consider all the negative terms, so negative multiplied with negative will be what? It will be a positive value. So positive multiplied with positive is positive, whereas negative multiplied with negative is a positive value. So therefore, what happens is based on the multiplication parameter, you are identifying whether the carrier signal is present here or not. So here, if you just see, if you're multiplying 0 with anything, you will be getting a 0. But when there is some say signal present and you are multiplying it with the carrier signal, you are getting some values over here. So here indirectly what you're doing is you are trying to implement the demodulator part. So it is like you have the product modulator. You have the product modulator. You're taking that and multiplying it with the carrier. So in that case, what is happening? At the receiving end, you identify whether in a given bit duration the bit is whether the signal is present or whether there is whether the signal is absent or whether it is present. That is what you are trying to do over here. And in this process, what you're doing is you are increasing the energy content which is present over here. So it is like you are amplifying the thing also, and you are checking, you are obtaining whether the signal is present or not. Now what I do is, once I get this information, I have to make use of the filter. I have to make use of this filter. So in order to obtain this filter, if you just see the block over here, you can just see what all things are present over here. So you can see some specifications are provided. So let us see what I'll directly use the filter over here. So this is the product result. This is the result of the product, that is ASK output multiplied with this original carrier. So I am getting some information over there. So from that information, if I pass this signal which is obtained over here through a filter, whether I'll be able to get back the original information. That is what I have to check out. So what I do is I use a digital filter design. So this is the digital filter design block which I'll be utilizing. To this input, I'll give the result of this product. I'll give the result of this product. And this output, I'll connect it to the scope. So now what I'll do is I'll not alter anything. I'll just try to run the entire stuff. So once I have run it, I'll just change the layout. So this is your message signal. This is the carrier signal. This is the ASK output, what you are getting. Whenever 1 is there, carrier signal is present. Whenever 0, the carrier amplitude is suppressed. And this is the result of the product of ASK with the carrier signal. Now this one, you are passing it through the filter. Now in a filter, what I try to get is, I try to get back this original information. That is, I try to identify the energy content, and then I try to decide whether it is logic 1 or 0. So here, if you just observe what is happening, the filter is taking the input and it is providing you some result over there. And now instead of this, here I'll try to make some changes. So what is happening is, I'll I'll consider a low pass filter, since it's a low pass signal over here. I'll try to increase the order. Say I'll make it as 50 and see what happens. I'll try to see what happens. So I have done this. I'll come to the scope. Again, I'll run it. I have changed the order. So what is happening if I'm changing the order? It is, if you just observe, a very slight change you are able to make out. So now any other parameter which I can change over here. So what is the pass frequency I'll consider? So what I'll do is I'll consider a pass frequency of 0.01. Let us see, let us keep the stop frequency at that point, if and see whether I'll be able to get the result. So still no changes. So again, I'll come back and I'll try to change, say this parameter, I'll reduce it. So I'll design the filter. So I have done some changes. I have obtained these. So I'll run and see. So here you can see that some changes have happened when I have changed the filter parameters. So what all things I changed? I changed the order. So previously it was 10, 16, I increased it. So here again, I changed the pass band point and the stop band point. So again, what I'll do is I'll try to increase the order to 100. So let me see what happens in that case. So if I increase the order to 100, so I am able to get back the original information, but with slight distortion. So this distortion is okay. So what is the output of this filter? Actually, it is nothing but the demodulated signal. That is what I can specify. So when I observe this, so we can see message signal, carrier signal. This is the ASK output. This is the product of ASK and the carrier. And this one is trying to get back the original information. So if you want to get back, you have to reduce the shift and all. Then what you do is you try to alter the filter parameters. So if I try to make this as 0.01, so I don't know what will happen now. So you have to analyze all these things. So what is happening? You are getting this parameter. Say I'll make it as 0.1. So let me see what it's. Okay, but I'm able to get back the information, but what is happening is there will be a slight shift. So the dispersion is happening. So you are able to estimate, you are able to get back this information. So if you try to measure the energy content in a given time period, and if it happens to be above some threshold value, then it will be indicated that it is logic 1, and if it is below some threshold value, it will be indicated as logic 0. And suppose there is some error in the detection, then I can go ahead with the information theory coding aspect, wherein I try to see whether I'll be able to detect the error, and if possible whether I'll be able to correct the error. So in order to do that, you have to apply your information theory coding aspect. So you alter the filter design parameters and try to obtain some results. Okay. So alter those parameters and try to get the result over here. Okay. So this is what we are getting. So this is ASK result. I'll try to see whether I'll be able to get back the original information. Okay, in this case. So let us consider this one. So in which I'll be putting in the relational operator. So it is like you have got the result of, sorry, not this one. So here you can see that you have identified that say possibly 0 is here, 1 is here, so that you have obtained after the demodulation. Now I want to identify whether it is 0 here, 0 here, or 1 here, so that I'll try to identify and try to see whether I'll be getting this original information. In order to do that, what I do is I pass this through a comparator. If it is above 0 or above some value, then what you do is you consider that for that entire duration it is 1, and if it is below some value, you consider that it is logical 0. So that you can perform by using the relational operator. So in this case, we have the relational operator. So relational operator output is connected to what? Output is connected to this filter output, to this filter output. And what I do is I compare it with a constant. I compare it with the constant. So what I'll do is, since we had seen that it is in the range of 0 to some value. So what I'll do is this constant value, I can consider it to be 0.2, 0.1, 0.4. So at present, what I'll do is I'll just consider it to be 0.4. So I'll assign a zero point 0.4 constant. So what this does is this compares these two and gives you the result. So what is the comparison I'll be checking? I'll be checking whether the result is greater than this value. So whatever filter output I'm getting, whether that is greater than this parameter. If yes, then it has to be logic 1. If no, it has to be logic 0. So you're basically setting the critical value over here. So now I'll connect this output to the scope and see what I'll be getting. So I'll run this. So when I run this, you can observe that what parameters you are able to get. So if you would try to adjust this constant, say I'll make it as 0.1. So let me see what changes will be happening. So if you just observe, there is a dispersion which is happening over here. From here, I am not able to start the identification. So what changes will be happening? So this has reduced. This has reduced. So that is, if you adjust it to very low value, it will be a problem. Entire thing might be identified as a logic 1. So I have made it as 0.01. So let me see over here. So if you just observe, I am able to get, but what happens is this, in the given bit interval, you have more of this dispersion. Therefore, what happens is errors might be introduced. If you have to reduce this, then you have to change the design parameters, then change this constant value. Okay, if you want, I'll make it as say 0.6. So if I increase it, let us see what happens. So if I have increased it, it is actually 0.6. So because if you just observe here, the output of the filter is less than 0.6. So it will never go beyond that. So I have to adjust it over here. So how much will keep? We'll keep around 0.45. Let us see what happens. I keep it in the point. So it is 0.5 maximum, 0.55, 0.52 something is the maximum value. So here we can observe that we are able to obtain this parameter. So in a given bit duration, if it is energy is high, it will be logic 1. If it is low, it will be logic 0. So you can adjust this value and try to obtain the results. Okay. So this is what we are getting. Okay. So this is the overall result. So this is the ASK result what we are obtaining.